is anode. अच्छा विवेक जी आइए आप इस झारसुगुड़ा कॉन्फ्रेंस में. I will wish you a
No, I'll connect with you. I'll connect with you.
Thanks Vivek ji. Thanks. Okay, we will start in another. Yeah, it is already time. Okay, so let us start. We welcome Binuta Patra today. She is basically worked many years, 38 years in NALCO, and she has was with various projects and in R&D implementation, technology, quality control, energy optimization, and process innovation. And she has presented 26 plus technical papers at leading national and international journals and TMS, IXOBA, IBAAS, I will add it. She is also the holder of aluminium related technology. She is also holder of 3 patents. Okay, madam, 3 patents are there. Her international exposure also includes technical training in Tomago, Aluminium, Australia. Is it working still, or there are some issues are there with the power, Tomago? Okay.
I think I don't have updated.
And
I went long back.
Long back. Yeah.
Yes. I will tell you, Tomago is working.
Yeah, Tomago is working, correct. And R&D Carbon, Switzerland has a good experience, research depth and practical industrial insight into the work. Welcome, Binuta Patra. This is the online
so much. Thank you
presentation. We already have about 24, 25 participants, and there may be more participants may join. And your stalwarts of smelters, Pradeep Chaudhary, and
good afternoon, sir.
Samantha Lakshman,
How are you?
Mark
I'm
Dutis,
good. Yes.
everybody is here. Khalil Khajiji, everybody is here. So welcome to all of you. And I will request Priyanka to start the recorded presentation.
Good afternoon. I'm Binuta Patra, former Group General Manager R&D at NALCO. Today I'll be speaking on the impact of quality changes in calcined petroleum coke on anodes used in aluminium production. This topic is increasingly relevant as the industry faces challenges in raw material quality and availability. I would like to thank IBAAS for giving me the permission for sharing my views on this subject. Let me briefly outline the structure of this presentation. I'll begin with a short introduction to the Hall-Héroult process, followed by the manufacturing and role of calcined petroleum coke in anode production. Then I'll discuss key quality parameters of CPC and how they influence anode performance. We'll also look at the Indian scenario, associated challenges, and finally strategies to improve anode quality. As we all know, aluminium is produced through the Hall-Héroult process, where alumina is electrolytically reduced in molten cryolite. During this process, oxygen is released at the carbon anode and reacts with carbon to form carbon dioxide, while molten aluminium is deposited at the cathode. The carbon anode plays a dual role. It acts as a current conductor and is continuously consumed during electrolysis. Now, coming to the raw materials for pre-baked anodes, calcined petroleum coke or CPC is the most important raw material in anode production, contributing nearly 65% of the composition. The rest are coal tar pitch and recycled butts. Properties of CPC directly influence anode quality and ultimately smelter performance. However, in recent years, CPC quality has been changing due to increased use of lower cost, high sulfur crude and growing demand for aluminium. So before we enter into the actual subject, I thought it's extremely important that we talk about the journey of calcined petroleum coke from a petroleum refinery, where it is not very much wanted and till it reaches the aluminium industry, where it becomes the most wanted raw material, most needed raw material for anode making. So the CPC starts its journey from the crude oil refining unit, where the residue is sent to a delayed coker to make RPC, that is raw petroleum coke, and this raw petroleum coke comes to a calciner, where where you get calcined petroleum coke, which ultimately becomes the raw material for aluminum industry. And if we take around, say, 1 ton of crude oil for processing, we get around 40 kg of CPC for the aluminum industry. And quality of this calcined petroleum coke is affected by choice of crude, initial refinery process steps, coking and calcining processes, handling systems between the refinery, calciner, and final customer. Now I'll just share the subsequent slides, which will have a brief about all these unit operations for better understanding, because ultimately the CPC quality depends on the refinery process, it's the origin of the crude oil, and also the calcination process. So coming to the refining process, as you all know, when the crude oil is refined by this distillation processes, atmospheric and vacuum distillation, to give us valuable products like which is of which is of interest to the refiners. So these are of commercial applications, that is gasoline, naphtha, kerosene, diesel fuel, and gas oil. And the residue which is left out is it goes to delayed coker. It becomes the feedstock for the delayed coker, from where we get RPC. So the chemical properties of RPC, such as sulfur and metals, are directly related to crude oil quality. Now, looking at the delayed coker, what happens here is converts low value residual oils into higher value lighter products. Final carbonization occurs in coke drums at higher temperature and pressure. And physical properties of RPC, such as volatile matter and moisture, are related to the operating variables of delayed coker. And we get three products out of these delayed coker. That is short coke, which has high CT and shiny exterior and spherical in shape. And we have sponge coke, that is anode grade coke. They have a well developed pore structure, lower CT, that is coefficient of thermal expansion, and preferred for the aluminium anodes. And then needle cokes, they go to go for graphite electrode manufacturing. They have needle like structure, lowest CT, low metals, and sulfur. Now coming to the calcination process, where RPC is converted to CPC. This is nothing but a thermal treatment process at a very high temperature, say 1250 degrees centigrade, where the moisture and volatile matter are removed by heating, and which increases the electrical conductivity and density of the RPC, and it becomes more oxidation resistant and becomes suitable for anode making. And the calcination operation has a significant influence on CP coke quality. Cokes with substantially different volatile contents in both quality and quantity and impurity levels should be calcined under different conditions. And the methods of calcinations are rotary kiln, which is most widely used, and rotary hearth furnace and vertical shaft kiln. Then what happens to this RPC when it gets converted to CPC is moisture gets removed, volatile matter gets removed, ash reduces, fixed carbon increases, and the impurities they change as per the operating variables of the calciner and the equipments. And the real density and bulk density, they improve, they go to higher values, and the strength improves, and the apparent density also increases. Now the CP coke enters the carbon plant of the smelter plant from where we make anodes. And there are three stages of production of anodes. That is green anode plant, baked anode plant, and then roller anode shop. And I'll just briefly just give you the process. The coke upon reaching the carbon plant is graded into different fractions and crushed and ground into fines to give you the desired fractions as coarse, medium, and fines. And then it is also mixed with the crushed spent anode butts, which comes out from the electrolysis cell after consumption of the anodes. And then the dry aggregate is preheated and is mixed with coal tar pitch at a particular temperature, say 150 to 170 degrees centigrade. It is formed into green anodes, and then it is baked very slowly for a period of say 14 days upon when the pitch gets carbonized, and it reaches a temperature of 1050 to 1120 degrees centigrade. And now the baked anodes become suitable for the electrolytic operation. And then they are rodded and sent to the pot line. In this slide, I've just shown the picture of three stages, all the three stages of anode making. And of course, this is the picture from NALCO. So it will be different for different aluminium plant and aluminium smelter plant. As we are talking about the anodes, it's also important to understand the anode consumption mechanism. From the overall reaction, which we all know, if we calculate the theoretical consumption of carbon from this equation by stoichiometry, it comes to around 334 kg of carbon. It's to be consumed per ton of aluminium production. However, this value is always on the higher side due to the first reason being the current efficiency being always less than 100, and also losses due to excess reactivities and dusting, breakages, etc. So we get a figure higher than 400 to 420 or 430 kg of carbon per ton of aluminium. And if we look at the schematic, if we say the mechanism we want to understand, if you take a schematic of a single anode and see how this carbon gets consumed, this is due to electrochemical formation of CO2 due to this overall reaction, and the formation of carbon monoxide due to back reaction. And then the oxy-reactivity, which happens at the top of the anode at around 400 degree, 450 degrees centigrade, where oxygen from the air reacts with carbon to form carbon dioxide. That is called air reactivity. And there is back reaction from the carbon dioxide gas underneath the anode, again reacting with the carbon to form carbon monoxide. That is called carboxy reactivity or CO2 reactivity. And there is, of course, preferential oxidation binder. The dusting also takes place inside the pot. So what we look for in the pre-baked anodes, what are the critical properties? These are high apparent density, high mechanical strength, low electrical resistivity, high thermal shock resistance, low chemical reactivity, and high chemical purity. And these anodes are tested for specific properties, which gives us an idea as to what kind of anodes we are using in the pots. So which tells us about the apparent density, specific electrical resistance, flexural strength, compressive strength, coefficient of thermal expansion, fracture energy, thermal conductivity, real density, air permeability, and reactivity figures along with the impurities. Also, I wanted to share with you one theoretical equation of carbon consumption, where these anode properties affect the are related to the net carbon consumption, and along with the some part parameters like current efficiency and design cell one cell factor depending on the design of the pots and bath temperature of the pot. Let us have a look at the quality aspects of calcined petroleum coke and their impact on anode quality. So the CPC, the properties which are tested for CPC are apparent density and the real density, the impurities and the reactivity figures. And the apparent density, as you know, it affects the Big density of anodes, and anode cycle is decided based on the Big anode density. And real density indicates the calcination level of CPC, and baking level in anode making is adjusted. And sulfur, it affects the net carbon consumption, reactivity figures, and baking levels adjusted for desulfurization. And it has also it leads to environmental impact. And the impurities, iron, silicon, vanadium, nickel, all these lead to metal contamination, and especially vanadium leads to air reactivity. And sodium and calcium, they affect the reactivity figures. And size and grain stability, they are important as far as the structure of the anode is concerned. So why and how is coke quality changing? So refineries on average are running more lower cost, high sulfur and heavier crudes, sour crudes, which directly impact coke quality. A significant increase in aluminium production and demand for coke is not being matched by growth in traditional quality anode grade cokes. So if we look at the Indian scenario, today the aluminum capacity in India is 4.1 million tons. It is projected to be 8 million tons. And so the CPC requirement is going to double from the current 1.3 million tons to 2.6 million ton. But the challenges are like limited availability of low sulfur RPC. Only 5 out of 23 refineries produce anode grade RPC. So there's a domestic supply gap. So above figures may not be up to date. It's an old slide. Now let us see the changes seen in CPC quality and the impact on anode quality and smelter performance. So there are four risks which I'll be explaining. So first is decrease in coke density due to crude changes and higher volatile matters. Cokes with more isotropic structure may be used, while short cokes may be blended. Increased impurity levels, particularly vanadium, and sulfur levels of high sulfur cokes used in blends will increase. So in the next slides, I'll explain each of these risks in detail and what are the impacts on anode quality. So first, let us have a look at the coke bulk density. If it decreases, it has a direct impact on big anode density. Anode shift life is going to be affected. Increased anode production cost. Air permeability of anodes will increase, leading to increased carbon consumption. And specific electrical resistance will also increase, leading to increased power consumption. Here I have shown a few graphs where you can see the bulk density of cokes is directly related to the apparent density of anodes, and also if the bulk density decreases, the air permeability of anodes also increase. Now let us see the impact of isotropic cokes, which has low CT on anode quality. So here I've shown some graphs where it shows that if the CT of coke is high, that affects the CT of anodes. That is also going to be high on the hat side. And then there is interdependence between the grain stability of coke and the flexural strength of vibrator. These vibrator and pressed anodes have also are shown in this graph, where you can see that grain stability of coke, if it is higher, the flexural strength becomes higher. So and flexural strength is related to the CT of coke. The presence of short cokes in CP coke matrix will lead to production of anodes with higher CT values and lower flexural strength, and possibility of development of anode cracks during electrolysis. Next, let us see the impact of increase of vanadium in CP coke on anode quality. In fact, vanadium is a catalyst for air reactivity, and increased vanadium in CP coke leads to higher air reactivity in CP coke and lower air reactivity residue in anodes. This graph, the correlation is shown here, where if vanadium is high, the air reactivity residue decreases, and also if vanadium is high, reactive coke itself gets affected, and it affects the air reactivity residue of anodes, and this may lead to increased net carbon consumption and carbon dusting, and possibility of ion contamination due to bath flooding in tap door and anodes is also possible due to air ingress, and of course vanadium will lead to metal contamination.
Now let us see the impact of increase of sulfur in CP coke on anode quality. Increased sulfur leads to increased net carbon consumption due to net loss of sulfur. And as you can see from these graphs which I have shown, the high sulfur, the anodes made out of high sulfur coke, they start desulfurization at around 11 after 1100 degrees centigrade. So desulfurization leads to increased air reactivity, increased permeability, and increased net carbon consumption. And it also poses environmental challenges in terms of emission of SO2 gas. And the only positive thing we notice is the CO2 reactivity residue will show better results when the sulfur is on the higher side in CP coke. But again, the effect of recycled sulfur on electrolytic bath and current efficiency need to be assessed.
The impact of increase of sulfur in CP coke on anode consumption and current efficiency has been studied in detail, and it has been published in a recent publication in 2023, and the results of which show that when the sulfur content in anodes increases, the carbon consumption also increases, and also the sulfur content, when it increases, it and the current efficiency gets affected, and it has a downturn when sulfur in anodes is on the higher side. So the results have shown that current efficiency lowers by around 1.3% per 1 weight percent of sulfur, and carbon consumption increases by 6.1% per 1 weight percent of sulfur for pre-baked anodes. We did some R&D studies towards improvement of anode quality at smelter plant of NALCO, and the studies which I'm going to share with you have already been published in relevant publications, and the reference data would be of interest because the whatever experiments have been carried out, they are specific to NALCO parameters, NALCO process conditions.
So NALCO has 180 kiloamps aluminium Peshini technology pots with an annual capacity of 4.6 lakh ton aluminium, and we have fume treatment plants and GTCs, gas treatment centers. We have two plants, two carbon plants to manufacture anodes, and our anodes are 1415 2000 into 550 dimension, 1180 kg of weight, and the cast products are ingots, soles, wire rods, strips, pellets, roll products, tea ingots, and checkered sheets. So the CP coke, which was taken for the R&D studies, were of two types mainly. One was of higher density with lower impurities, and another was lower density and with higher metallics and higher sulfur, and of course, and also higher reactivity. The first experiment carried out was to see the effect of blending on the resultant anode quality, and we did the experiments by blending the 30 to 40% of premium, the higher grade coke, all fractions with the lower grade coke, and anodes were made, and all these experiments were carried out in R&D carbon equipment, bench scale equipment, which is supplied by R&D Carbon Switzerland. So these bench scale experiments showed that there is considerable improvement in anode density, green density, and bake density of the blended anodes. The second experiment was to see the how to improve the reactivity figures. This, of course, it is difficult to implement in the plant with the present setup, but still we tried to see if the whole of the fines fraction can be made from the premium grade coke, and the dry other fractions are of the lower density coke. Because the fines fraction is the most reactive part of the dry aggregate, so if that fines is the fines of the premium grade coke is used in place of the lower grade coke, so its effect was as expected. The reactivity residue increased from 65 to 85%, and carboxy reactivity also increases from 79 to 84%. Then the next experiment was carried out with respect to again the fines. So minus 200 mesh was operated at 68 to 70%. That was increased to 80%, around 80%, and accordingly the blend number was measured, and it was found that it is increased to from 3500 to 4400. And as you can see, the blend number is, as you increase the blend number, it also increases the density, baked green anode and baked anode density. So it is always preferential to work with higher surface area fines and lower fines, lower percentage of fines, and play with ultrafine content and GYS ratio for getting anodes with better density. The mixing temperature was also increased in the bench scale plant experiments. We increased the mixing temperature, and we tried to make anodes at different mixing temperature, and we could see that at the higher the mixing temperature, better is the density of anodes. It is natural because the pitch is able to ingress into all the pores of the coke, and it gives a very good structure in terms of density. And then as to mitigate the effect of reactivity issues, mainly attacking on the AR reactivity of anodes. We did extensive studies trying various additives to see their effect on decrease in air reactivity losses. And we found out that boric acid is one of the inhibitors which gave us very satisfactory results in lab scale and pilot scale and plant scale limited plant scale trial. And then we implemented in the whole plant, and now in both the carbon plants this process has already been it is in use and it is in operation. And the results which I'll show you, the air reactivity before addition of boric acid residue used to be around 62 to 63%, and after we started adding, it has come to a value more than 85%, and accordingly the air reactivity dust is decreased. And of course, when you are adding boric acid, there has to be some increase in boron content, so that needs to be monitored. And of course, average metal purity, there was no effect on average metal purity. And this actually, boron in metal, it again depends on the vanadium from other sources also. So this needs to be wherever, suppose someone wants to add this boric acid in their plant, so it needs an extensive trial and study before implementing the same. And the results which I'm going to share is that the net carbon consumption was found to have reduced by 3 to 4 kg per ton, and accordingly this is calculated value of CO2 emission reduction by 13 to 14 kg per ton. And at that point of time the saving was around 7 crore per annum. And then another experiment was carried out at the CP coke calcining plant, where we added this boric acid powder at the discharge end of the CP coke when it was still in the hot condition. We just mixed it physically and took out that coke. And the coke, when we analyzed the CO2 reactivity and air reactivity had decreased to a considerable extent. And this coke was again used for bench scale experiments to make anodes and find out the effect on the reactivity figures of the anodes. And there was considerable improvement in air reactivity residue and carboxy reactivity residue. Before I conclude my lecture, I would like to just share one slide with you on inert anode technology. So as you all know, the companies such as Rasal and NALCO, Rio Tinto, LSS are developing inert anodes. If successful, this technology could eliminate carbon-related emissions. As per latest reports, commercial scale experiments are being carried out at Rasal. However, full-scale commercial implementation still remains challenging. Thus, the role of carbon anodes used by the industry at present demands focused attention. And here I have given the references. Now I will conclude my lecture by sharing some strategies to mitigate the impact of quality changes in CPC. So I'll give some suggestions, which of course are not exhaustive. Maybe some other better suggestions may come up. But these are my views based on my experience. So there will be 2 slides for these strategies. One will be for the calciner, coke calciner end, and another will be for the smelter plant. So for the calciner, at the calciner end, the key quality measures would be understanding quality impact. That is, co-calciners must have a clear understanding of how CPC quality influences anode characteristics and consequently the overall efficiency of the electrolysis process. So this is extremely important because if there is no alignment between the calciner and the smelter, so there will always, will be cases where off specification material will reach the smelter and we have to use it and have a deleterious effect on the process. And optimize blending of RPC, ensure proper blending of RPC from multiple sources to consistently meet anode grade calcined petroleum coke specifications. Controlled calcining temperature, maintain strict control over calcining temperatures tailored to the volatile matter content and impurity levels present in different RPC batches. Consistency in CPC supply. Supplying CPC with consistent and appropriate quality is critical for stable downstream performance. Stringent quality assurance. Implement robust quality control systems and rigorous testing protocols at the calciner stage to ensure reliability and uniformity. Now, key considerations at smelter end would be strategic coke blending at smelter level. That if the smelter is getting CP coke from multiple sources with different quality, that is higher density or lower density, and higher impurities and lower impurities. So smelter should adopt a well-defined blending strategy to minimize variability and ensure uniform anode performance. Optimized baking parameters. Strict control of anode baking temperatures is necessary to achieve desired physicochemical properties. Improved anode covering practices and process monitoring. Adoption of better covering techniques along with real-time online monitoring systems can significantly enhance anode quality and reduce defects. Robust quality control systems. Implementation of stringent quality control and testing protocols at smelter is critical for maintaining consistency. Optimization of fines in dry aggregate. Reducing the percentage of fines while maintaining a higher blend number can improve anode density and strength. Higher green paste mixing temperature where feasible. Increasing mixing temperature can enhance binder distribution and improve paste homogeneity. Use of additives. Incorporation of oxidation inhibitors, anode coatings, or other additives may be considered based on operational requirements. Development of tailored CPC specifications. Formulating CPC specifications specifically suited to the needs of the Indian aluminium industry will help address raw material variability and improve overall smelter efficiency. Thank you for your attention. Thank you all.
Excellent presentation by Madam Binuta Patra. So now the session is open for discussion. Please, you are free to ask questions. Please go ahead. Anybody? Questions?
Yes, I have a very simple question.
Mark.
Yes,
I'm just back from India. I visited NALCO.
Okay.
And they complain about anode quality, and their spec is exactly the spec of your coke property with high vanadium. They have 20% loss of carboxyl resistivity. So I have to understand that they are doing that on purpose because you have all the knowledge to explain that what's happening. And this is preventing the smelter to increase the amperage of the smelter to 220, for example. That will be easily achievable with a good anode. So explain to me the politics of this because it's making no sense to me at all.
I couldn't get your question, exact question.
Okay, I will go slowly.
Yeah.
I'm just back from India.
I got it. You visited NALCO and you saw that anode quality.
I saw the spec of the anode. The spec of the anode is
yes.
exactly the one of the bad coke with high vanadium, 20%
Yes.
carboxy resistivity loss.
Yes,
And
yes.
this-
that I'll explain why the spec is kept at 0.25. I think vanadium is 0.25 because the availability, the sources in India, when the vanadium is lowest only in the northeast region, Guwahati and Numaligarh coke. Okay, where you get around 0.02 to 0.03. That is 20 to 30 ppm. But the production is very less. Maybe 40 to 50,000 we are getting from there. Other suppliers like RCI, the rain calciner, other suppliers are there, who get the RPC from outside, from Indonesia or from other regions, and they blend it. But they do not take Indian source also. They only blend it and give it to us. And they play on the cost, and always we get vanadium at the border of the specification. And that has been happening all these years. So, it's very difficult to lower the specification. So that is why what we do is we blend it. I mean, strategically, we procure the material in such a manner. Of course, blending is very difficult in smelter because it's all in silos and only we play through the bottom silo feeders. And we keep we dedicate one particular silo for the better quality coke and the other two silos for this higher vanadium coke. And that is why we have introduced this boric acid to mitigate this.
Well, it's not working enough because you're getting 20% loss on carboxy resistivity, and this is preventing the anode. The anode is not good enough to increase the amperage in not even to 185. That was done in the past, but they are not possible anymore to do that because of the anode.
Carboxy is a different story. It depends on the baking level. If they are not maintaining baking level properly, then carboxy is not related to air reactivity, but carboxy is mainly related to the baking level of anodes and sodium. If sodium is not controlled properly and this baking level, these two affect the carboxy reactivity.
Okay.
So I am not there in the plant since
No, I know you're not there
2017.
anymore.
So
But they need help, or
since
they,
2017.
either they do it
what
on purpose or they need help, because right now they are a very bad situation in terms of anode quality. Okay, thank you.
Okay, thanks, Binuta.
Thanks.
Mr. Khalil Khaji.
Yes, Madam Binuta Patra,
Yes,
presentation
sir.
was a good one.
Okay.
Actually, the big change in cokes is sulfur content, as you have mentioned in your presentation.
Yes.
And I was looking at your slides. Somehow, probably you missed adding electrical resistivity.
Yes.
Sulfur has an impact on the anode electrical resistivity. So that maybe you can add in your presentation, in future presentation. Its impact on.
Yes, sir.
Then,
I have read your paper. You presented it in IXOBA. I have read your paper and somehow I missed it. I wanted to add it as a mistake. Yes.
And one more thing, as Mr. Mark was pointing out, anode quality is not yet suitable for amperage creeping.
Amperage increase. Yes.
Yeah. What I saw is that the densities are rather low, and green density I read in one column 1.645, and baked was 1.5, something like that, 1.55.
Yes.
This is a big difference. There is a big scope for improving the density, because this is required for creeping of the current.
Yes.
So this one aspect is, and the coke quality you showed in the presentation was good. I won't consider vanadium 300 ppm vanadium as a bad coke. It is acceptable coke. Nowadays, all over the world, it is going even 350. So 300, you are lucky. You are having between 220 to 300
Yes.
ppm vanadium. Just observation, I told you.
Yes, yes. And the density part, sir, I will tell what happens is in NALCO, we have 2 carbon plants. The old one, I know you were also working there when I think commissioning stage you were there. So the list mixer is still existing last since 1985, I would say. So that is if you do any modification, even in vibro compactor, anything, the density, I mean, mixing is 147 degrees centigrade. So the density remains very low in that plant. The other plant where you have this bus mixer, the new carbon plant, you get better anodes than the carbon plant 1. So
Okay.
the story
Okay. Thank
goes
you.
like this.
Thank you.
Ma'am, where
Madam.
these anodes are used? What is
Yes,
the
Hello?
madam. Yes, madam.
yes, where these anodes are used? What is the utility and application of these anodes?
Anodes are basically they are the current. They are used in electrolysis process. If you see my slide, I have explained the Hall Herod process, where you have to have positive current for the electrolysis, where carbon anodes are used.
Can they be used in arc furnaces, etc.?
Pardon?
Arc furnaces or
No, those are not suitable for aluminium production of aluminium from alumina. So for commercial, this is the commercial process for production of aluminium.
and one more thing is that nowadays the vanadium and its oxides are being substituted by niobium. So have you ever considered it for your application in making anode or like?
Madam, I think you are talking, when you're not talking about aluminium, like neodymium and all, that is not here in our vanadium. We are talking about it. There's an impurity in the carbon raw material.
Okay.
Okay.
Okay, thank you, ma'am.
Okay, Mr. Vivek Saxena, please.
Yeah, madam, nice presentation, and it
Thank you
brushed
so
up
much.
all the things. And just one question regarding one of the slides you presented, that where this boric acid was added into the coke production itself.
Yes.
At that time, some parameters were there. So did we change the calcining temperature also at that time?
Calcining or baking?
Calcination temperature. I mean, heating up to that level. Why I'm asking this? Because the pertinent question is sulfur. So if we are able to, mitigate that sulfur ill effects, and also with this boric acid good effects, then this will be the perfect case.
No, actually, that was a very short span study. We were just focusing on this impact of vanadium only and the area activity. So we didn't consider studies on sulfur and calcining conditions. That was normal condition only, normal calcining temperature in rotary kiln.
One more question I have. Probably in India, we don't have electrically heated kneader. So I was just asking, maybe Haji sir is here, maybe he can add value to this. What is, I mean, say we are having this electrically heated furnace, the kneader. So the effect on electrical resistivity with respect to this, because there is a gradient which gets inside. So is there anybody who's having experience of having electrically heated kneader with respect to the properties of anode in terms of electrical resistivity?
Khalil Khatiji, please.
Yes, it is a very good question. Now, Actually, BUS are offering electrically heated kneaders. It is a change from STM heated mixers. So in these heaters, you are regulating the temperature very well. Now, your question of electrical resistivity, whether it improves the electrical resistivity, it is like this. Let me explain you. When you, after all, the role of the electrical heating or the STM heating is to keep the paste at a certain temperature. Actually, you can have a good control in the electrical heated kneaders, and also you can have a temperature gradient in the mixer itself by adjusting the heat input at the beginning of the kneader, middle of the kneader, at the discharge point of the kneader. It is possible. But in the mixer itself, there is a friction between the particles and there is a heat generation, actually. So, well, I would say the electrical resistivity, if you are looking for the improvement of the electrical resistivity, we need to increase the temperature of the paste. I will explain you why. When you increase the temperature of the paste, you are reducing the viscosity of binder. Binder, when I say, I don't say only coal tar pitch, but it is a mixture of fine particles and the pitch. So this binder, especially when you have more of ultrafines, the viscosity is very high, and when you increase the mixing temperature, it has a very good effect of reducing the viscosity of the binder. This helps the binder to coat the particles and also to push the these binder material into the pores of the coke particles. So when you do this, the connectivity between the particles, when you compact, the density increases or the connectivity of the particles improves. So the flow of the electrons, after all, what impacts the electrical resistivity is the flow of electrons. Because the connectivity improves because of the increase in the density and better coating of the particles, you get a better electrical resistivity. So I would suggest, if it is possible in the expansions, to go for electrically heated kneaders. They are you can have a better control, you can have a higher temperatures in the mixers if you like.
Yes.
That way it might help you to improve the electrical resistance.
Yes, sir. Kari sir, that is exactly what I was also, you seconded my thought. So that was the thing I was also thinking, like if we increase that with respect to electrically heated meters, then electrical resistivity will come down.
Yes, true, very true. Because just to tell you, electrical resistivity is impacted by many things like this density, how much pitch you have added, and also the sulfur content and the way of forming the anodes. Not only at the mixing the temperature impact, but also you should consider vacuum vibrocompaction, because at higher temperature you have more release of volatiles, and that can be evacuated by using the vacuum. So vacuum vibrocompaction helps you to compact the paste at higher temperature. So these all improve the density and improve the resistivity. Yeah.
Thanks, Mr. Khalil Khaji. So any more questions, Mr. Saxena, Vivek Saxena?
Thank you.
So Mr. Pradeep Chaudhary have some questions, please.
It is not just a question. Actually, I wanted to add something. Mark was speaking about this Kripes project for NALCO. All these things which Binuta has told that that list mixer is old. For a long time, we have been NALCO had been working to change the mixer, but it has not taken place so far. What I understand. But these are all part of the Kripes project. Changing the mixer, slotted anodes, then increasing the anode size, and then changing the baking cycle. All these are part of this Kripes project for 220 kiloampere, and I am sure when NALCO is going to have it, then they have to go for all this to increase that anode density as well as they have to work on the resistivity, and it has sustained for that higher kiloampere. So I think there is something that everything is in project actually. I don't know when we started the project, something to do about 220 kiloampere. We had all these things in that DPR to make large scale improvement in carbon plant. I am sure Binuta must have added something more in last 10 to 12 years. I'm sure that. So it is not a question that they cannot make it, but they have to go through the process. That's all. Binuta, I think you agree with me.
Yes, sir. Yes.
So I am not understanding why the list is not yet replaced. We have been talking about it for last 20 years, I think. The list
Yes, that 20 more than that, I think. I mean, 15 or so. Yes.
And initially, it was planned to use anodes from the second GAP, green anode plant, for the Kripes project. I mean, some parts were to be experimentally put on higher kiloampere, and for those we plan to use all those anodes from the second GAP2.
Yes.
I think that is what I wanted to add actually.
Thank you, sir. Thank you.
Very nice presentation, Binuta, and carry on.
Thank you, sir. Thank you.
So we have worked a lot many years together actually.
Yes.
Okay. So any more question, Mr. Gautam, Dr. Gautam Chatterjee? Any question? Anybody else have questions?
Yeah, I have a question.
Mr. Behra.
Yeah, I have a question. Say, it was a good presentation, Binuta. You may be knowing me a long back. Okay. So maybe 97 like that. Okay.
I think
so
in Incal we met in some.
Yeah.
Last Incal I met you.
Okay. So my question is, you say the world is facing crunch of this CP coke. The CP coke quality is deteriorating. So all these smelters they mix different grades to get good quality. When they're mixing, they do also innovation job on mixing, then grinding, then compacting. Everywhere they do innovation jobs. So my question is, does that bringing the particles to spherical size, is it helping to improve the density and to lower the electrical resistivity?
Spherical size, I don't understand where we get the spherical
size. Okay. I will make my question very simple, and this question may be to experienced people like Kaji Saab and Saxena Saab. So like this Solios had adopted a mixed crossing system. That is, they have gone for Rodax. And somewhere the mixture, they have gone major improvement. And also they adopted dynamic classifier instead of static classifier. All these improvements are coming in GP. So does this help to bring the anode density higher and to decrease the electrical resistivity?
This you're talking about Rodax process. As far as I remember, Rodax process is basically for making anodes for higher impedance spots where this grain to sand ratio is to be maintained. You do not crush the material much. You retain the grain of the
CP coke and the buds, and you have you come out with the anode with a better this thermal shock resistance. That is
Or is it
the
for
objective.
increasing the particle sphericality? They try to do, say, Rodax is not having a fixed cone, so it is also oscillating. So that gives the particles a spherical size. Is it true?
No, I cannot answer on this because I have not read about spherical size of the this thing, the CP coke.
Okay, okay.
Can
Mr.
I
Khalil
Because
Khaji.
it is already has pores.
Mr.
The
Khalil Khaji.
sir can add to it, Khaji sir, if he has some information.
the Rodax, as Binuta Patra said, avoids unnecessary crushing. It tries to keep coarser particles. It won't crush more than required. And as she rightly pointed out, it helps in maintaining high grain to sand ratio required for the thermal shock resistance of the anodes.
Okay.
But I have to tell you, because you were talking about the density and electrical resistivity.
Yeah.
The density is also affected by the coarse particles. Coarse particles you cannot have if you have too much coarse particles, the density goes down. Actually, there is a limit for the coarse particles. We have found out that particles bigger than 13 mm, content should be around 10%. Even better, it is between 8 and 10%. Suppose you go to 14%, 16%, 18%, your baked anode density drops. So to have higher baked anode density, you need to limit the percentage of 13 mm particles within 8 to 12%. Let us say 10% you will get. So Rodax has to crush in such a manner that not too much of big particles are there also. That is also one of the requirements. So Rodax, for a high throughput paste plant, Rodax are not performing that well. For 35 tons per hour paste plant, they are working well. But if you go to the 50 tons per hour paste plants, you need better designed Rodax plants or additional crushers to help the Rodax crusher.
Yeah, that means Lopanga.
Electrical resistivity, of course, is influenced by the density of the baked anode.
Yeah. Okay.
Yes, sir.
Thank
You
you,
are right.
sir.
That's why we are limiting the maximum course size to 12 mm only, and that to 6 to 8%. As Khaji sir said, it's only about 6 to 8% course scope.
Yeah, that is good. That is good.
Okay. Any more questions, Mr. Chaudhary?
No, thank you. It's okay. It's good. It's good.
Okay.
Good afternoon.
Thanks.
Good afternoon. My name is
Our lecture series of May is open. Anybody interested for delivering any presentation, interesting presentation, you are welcome. Mr. Khalil Khaji, Mr. Vivek Saxena, please consider. If you want to deliver any interesting topic, scientific topic, which is of common interest, please welcome.
Sure, sir.
Okay. Please consider maybe May, maybe June, because every month at the end of Friday of every month end, we organize this lecture series. This is for general interest and for mainly for companies to come forward and work together. Okay, Bhatta, how are you? Are you planning to present some paper, Bhattacharya, Devanand Bhattacharya? Your sound is not there.
Now it's okay.
It's okay.
No, in your IBAAS, I will present.
You will present.
In your IBAAS that seminar.
Okay, please come to Jharsuguda, the home of
So-
Mr. Vivek Saxena and Vedanta.
So one
I was
question,
thinking you are in-
Binuta, one question I had.
Yes.
Actually,
good afternoon.
for the selection of coke,
Yes.
what will be the criteria? Should we take a very high apparent density coke or medium? Because if our baking level is limited, so we cannot bake high. So then which type of coke we should select?
See, baking level, real density is important, not the apparent density. For baking level, you should choose a coke with real density 2.04 to 0.5 so that the pitch and the coke, they bake together and carbonize. But apparent density is not important as far as baking is concerned.
So should we take more than 2.05, 06, 07, say, real density
No, I
coke?
think 0.5 to 0.6 is okay.
Yes,
0.7
because
is becoming a bit higher side. Because some anodes are not also, if you consider the bake oven also, there is a difference of around 60 to 80 degrees centigrade from the least baked and the most baked. So this 2.05 to 0.6 is considered to be a better option.
Okay, thank you. So very good presentation. Thank you.
Thank you so much. Thank you very much.
Thanks
Good
to
afternoon.
everybody.
I have one question.
Yeah, please question.
Yeah, good
Anybody
afternoon. My name is Murthy.
yeah, please.
I am with XEGA. What I had seen in my experience with the data from the Patra side, when we increase the anode density, yes, definitely the baked anode weight, everything improvements, other improvements are seen. But towards the end of the cycle, when we measure the butt weights, there is no any improvement in the butt weight. That's how even the higher density anodes are leading to a more carbon consumption. So any particular reason?
Yes, if you look at the slides I've shown, the carbon consumption, it doesn't depend on the anode, anode density. It depends on other factors like reactivity factors, air permeability. Air permeability is of course related to anode density, but the density is not the primary factor for the consumption. It only decides your because once when you decide the shift cycle, it has to be both.
Yeah, I'm just saying for the same shift cycle. We're not changing the shift cycle.
Yes.
The
Because the
current everything is same. Only thing is we got a better density anodes, wherein the baked anode weight has gone by 2 to 3 kgs. Say 5
so you have to
kgs.
see the reactivity. You have to see the reactivity tests, how they look like, along with density. Many smelters, they do not test these reactivity figures because they do not have the testing equipment. What I understand, I don't know the present scenario, but those also need to be assessed.
Yeah, but when you look at physically the butts, so we find it a little more loose particles at the end of the life.
Yes.
It was not there earlier, when you get an anode, it is a very good anode.
Yes.
Everything is nice, but when it comes towards the end of the life, we see that testing and then loose particles with the so
that is a lot of reactivity, lot of CO2 reactivity, and if your baking is also not done to the extent possible, then you will have all those. I have some pictures I could not show that how if you mitigate this reactivity we have done during the experiment, how the surface looks like, even the underneath and the upper surface, if the reactivities are good, even with the lower density coke, lower density anodes.
And one more question.
And also during the end of the cycle, the temperature also rises. You have to see the bath temperature also. That affects a lot.
And one more question. So we were talking about increasing the higher temperature at the time of paste kneading. So that will give a better viscosity for the binder and give the coating and good density.
Yes,
So
yes.
and improve the electrical density because the packing will be good. Okay, understood. But
Yes.
about the, suppose if we do this, is there a chance for us to bring down the soaking time or soaking temperature in the baking kilns? Can we take an advantage there?
But why should we? You see, with the normal condition, if in the normal process parameters, if you're getting better results, then it's okay.
Mhm.
Soaking temperature, actually, that's also very important for the big donors properties.
That's true. So because
Yes.
this is going to help to reduce the electrical resistivity here. So the cycle time we can reduce it. No? I mean, if that is the case, if that gives an advantage without
Yeah,
impacting
but
the.
if you get better electrical resistivity, that is always
Yeah,
good.
that is of course the least the best. I'm not talking about just asking for like an experimentation. Is it possible to think on the ground and then do something? Because you are very experienced people in the carbon area, so just asking a doubt.
I think you should go. You should not compromise with the soaking temperature.
Thank you very much, madam. Thank you. Nice presentation.
Thank you so much.
Subhendra Nanda, sorry to interrupt. Subhendra Nanda has some question. Please. Mr. Nanda. Subhendra Nanda.
Okay, right now.
Yes, please speak.
See, you have really mentioned about the addition of inhibitors like boric acid. I would just like to inform you about what can go wrong. The boron, if it gets retained in the metal beyond a particular level, suppose you actually are making it in the form of an ingot. The buyer buys the ingot, makes it into a rolled product. Therein he adds actually grain refiners. As you may be aware, in a typical grain refiner, there is a ratio between titanium is to boron. If the boron content is high, this ratio will not work. So there have been instances, not exactly of this kind, but where particularly because of the fact that the boron in the metal was high, their normal grain refinement did not work. They have had to add aluminum, really 75% titanium in the form of ingot to ensure that the titanium boron ratio is all right.
Yes,
therefore, it is important that in fact at the cast house end, they must keep an eye on what is the increment in boron in the metal with time. Okay.
Yes, sir. I will just answer to your question. Like when we did all these trials, what we did was we optimized the boric acid addition so that the boron does not increase the limit of whatever is required for the cast house. And you also you have to see that what happens to the boron in the pot line. Actually, for wire rods also boric acid is added in the pot line in a few selected pots. That is different. But here what happens if you have vanadium in the metal, this boron also reacts with the vanadium to form borides, vanadium borides, B2B3 or B2B6, that goes to the sludge. So ultimately, yes, definitely monitoring is required and it has to be optimized. It should not exceed the limit of the cast products.
You see, essentially what happens is over time the boron would actually increase. the retained boron would actually increase with time. So it has to be viewed from that angle also.
Yeah, definitely, sir. Monitoring is definitely required in the cast metal when you're adding one additional, material into your matrix.
Okay.
Yes.
Thank you very much.
Thanks.
Nanda,
Hi, go on. Yeah, please.
boron also, it is very hard and it forms
Yes.
scratches in the foils,
All right,
those
right,
kind
right,
of
right.
products.
Right. Agreed.
Okay, so thanks, Binuta, for excellent presentation, good discussions, and we will continue to hold this lecture series, and we will invite some of you to come forward and make the presentation in the month of May or June. So I will request Mr. Khalil Khaji or Vivek Saxena or Mr. Nanda, please come forward and send your interest and send your topic for online presentation. Thanks everybody. Thanks everybody for this.
Thank
good
you,
presentation.
IBAAS.
Thank you.
Thanks.
Thank
See
you.
you.
Thank you.
Yes,
you.
Mr. Vivek Saxena, anything?
Thank you. I just wanted to thank you.
Okay.
Thanks.
We'll wait for your confirmation if you can present either May or June. So we will
Sure.
welcome you. Any general
Sure.
topic. It's not necessary to dive